welcome to this video where let us discuss a topic called as symbol by symbol detection of the data with controlled ISI. So if you have seen my last video where I have explained a design of a band limited signal with controlled ISI, or it is also called partial response signals, where we have discussed actually the two methods and the methods are like DuoBinary coding method as well as modified DuoBinary coding method. Now if I use those controlled ISI techniques, where by using those methods we can achieve a bitrate of say 2 W/Hz per second or 2 W bits per second. So by introducing the ISI, inter-symbol interference, so in the presence of that ISI, how exactly we can detect the symbols, okay, for both the methods, that let us discuss in this particular video. Now, coming to the first method, that is DuoBinary signaling method. As we have seen that DuoBinary signaling method is a method where the x of nt is actually equal to 1 for n equal to 0 and 1. That means two symbol intervals, you can have a x of nt equal to 1. So we have actually introduced interference or ISI into the particular symbol here. The two correspond to consecutive bits are allowed to interfere in the controlled manner. Okay, so in the presence of this, how we can detect the symbols? Okay, that let us understand in this topic. Now, for this particular case, I will take this example where this is actually the diagram for a DuoBinary signaling scheme. So what exactly we have used over here is a simple adder. Okay, so we are going to add the present bit. Let me say the present bit is AM, okay, and that is added with the previous bit at the previous symbol interval. Okay, that is AM and AM minus 1 both are allowed to interfere with each other with the process of the addition here. Okay, so that means the output will get a BM, which is nothing but it is AM plus AM minus 1. So by combining two symbols together, by allowing the interference between the two symbols together, we're actually transmitting the signal to the receiver. Now this ISI is introduced in a controlled manner between the present symbol and the previous symbol. Okay, so in the presence of that controlled ISI, how we can detect it, that we have to understand with the example which I will explain in the next slide. Now what is this AM is? AM is nothing but is a transmitted sequence of the amplitude. Okay, it can be like say +1 or -1 in the polar format. If I represent the bits binary data is either +1 or -1, that is 0 is represented as -1 and 1 is represented as +1. So this AM can have two voltage levels, either +1 or -1 with the equal probability. Okay, so by adding this with the previous bit, say AM with a AM minus 1, this BM will have three different voltage levels, that is either 0 or +2 or -2 with a corresponding probability of 1/4, 1/2 and 1/4 respectively. Okay, now since we are actually adding the symbols in the transmitter, in the DuoBinary signaling generator, in the receiver, simply by doing the opposite process, that is subtraction, we can get back the original sequence, or we can estimate AM by simply subtracting the bits. Now in this particular method, we face one particular problem, which again I will explain with an example in the coming slides. Okay, that is error propagation. So error propagation is the major problem. So what is that error propagation is, we will see in the next coming slides. But before that, let us understand this concept, okay, by using one example. Now just look at this example here. So I have taken a same figure. Okay, we are going to add AM with a AM minus 1. AM is the data sequence. Let me say the data sequence is this. The yellow colored one, say 0 1 0 1 1 1 0 1 0 is the data sequence AM. Okay, now if I represent, so suppose you want to add AM with the previous bit, I have to consider one reference bit. The reference bit is, say, if I begin with this as the initial bit here, I should be able to add this with the previous bit, right? So I will assume this as the reference bit here, 0. You can assume it as 1 also, no problem, either 0 or 1. Okay, so as I told earlier, AM is nothing but the polar representation of the data sequence or a binary sequence. Okay, so 0 is represented as -1. 1 is represented as +1 over here. Then AM is added with AM minus 1. That is, so this is the present bit if I consider at the first symbol interval. -1 is added with the previous bit. So -1 and +-1 is nothing but it is -2. Right? +1 added with -1 is 0. So -1 plus 1 is 0. Again, +1 and -1 is 0. +1 and +1 is actually 2. +1 and +1 is 2 again. So like that, you just go on filling this particular row. That is, BM is nothing but AM plus AM minus 1. Now, this signal is connected to the channel, it is transmitted at the receiver, and in the receiver we have to detect, as I told earlier, just a subtraction of the received symbol with the previous data. Previously estimated data will give you the current data. So that means estimated symbol is nothing but, that is AM cap is nothing but, it is BM minus AM cap minus 1. Okay, that is BM. Assuming that this symbol is already recovered, because somewhere I have to start my detection actually. So this is the present symbol what we have received, or present voltage level, that's what we have received. So this minus 2 is actually subtracted with minus 1. So minus 2 minus of minus 1 is nothing but it is minus 1. 0 minus of minus 1 is nothing but it is plus 1. 0 minus plus 1 is nothing but minus 1. Like this, just go on again filling this particular row. Okay, now minus 1 is treated as 0, plus 1 is treated as 1 in the polar format. So right, just go on converting the polar representation into the bits here. Minus 1 is 0, plus 1 is 1. Now just check the data sequence whatever we have here, okay, in the transmitter, and the detected or decoded sequence, both are actually same. So in the presence of noise or in the presence of ISI, we could be able to recover back the original data. This is actually DuoBinary signaling method. Now I told earlier that there is one problem. We actually face one problem, that is called error propagation. Now just look at this particular example here. I have taken one more example, okay, so where my reference bit is again 0. This is the data sequence. I have completed this task already, okay. Let me say DuoBinary output is minus 2, 0, plus 2. That means you are actually having the voltage levels, 3 possible voltage levels. They are either 0, plus 2 or minus 2. So these are the voltage levels we are going to get in the DuoBinary signaling method. Okay. Now just look at the received symbol. This is transmitted DuoBinary output in the receiver due to some noise effect. Okay. Here we have received same voltage level 0, 0, plus 2 as plus 2 only, 0 as 0 only. Just look at this case. So this is the error, right? 0 is represented as plus 2. That means because of the addition of some noise, actually my received symbol is not same as the transmitted symbol. Okay, it is plus 2, and this again same. Now due to this, if I apply this to the receiver, okay, where I estimate the symbol by subtraction process, minus 2 minus of minus 1 is minus 1. So this again subtraction is 1, no problem. Just look at this point now. 2 minus 1 is minus 1, right? 0 minus of minus 1 is plus 1. 0 minus of plus 1 is minus 1. Now when I again represent the minus 1 as 0 and plus 1 as 0, I mean plus 1 as 1 and minus 1 as 0, yeah, minus 1 as 0 and plus 1 as 1 if I represent it here. Compare the transmitted sequence or data sequence with the received sequence, they are not same. Because of this error, okay, error at the particular symbol interval, okay, now 1 is translated into 0, and now the same error is actually propagated to next symbols also. Just look at this. We have the error only at this instant of time. Here during this symbol interval we received actually the correct voltage level, but when I decode it, the error is propagated to other symbols also. This is the major drawback of the modified DuoBinary encoding method. Now to overcome this particular problem, as I told earlier, this is the error propagation what we have. To overcome this particular problem, we have to go for what is called a modified DuoBinary signaling method. Okay, same DuoBinary coding method. Just look at this diagram here. This is the DuoBinary coder, whatever I have used in the previous slide. This is the DuoBinary coder. This is the DuoBinary coder where we have an adder and a delay network. That's it. So we have an adder and delay network over here. Okay, and this is preceded by something called as a precoder. Okay, a pre-coded DuoBinary scheme. A modified DuoBinary signaling method is nothing but it is the pre-coded DuoBinary scheme. Okay, a precoder consists of what? A modulo 2 subtractor basically. Okay, it is a modulo 2 adder, even though it is written, we are performing a modulo 2 subtraction, but modulo 2 subtraction and modulo 2 addition are same. Okay, only in binary case, that is modulo 2 case. If it is modulo m, subtraction is different. The method of subtraction is different. But under the binary scheme, modulo 2 addition is actually same as modulo 2 subtraction. So what we have here, we have a XOR function which performs a modulo 2 subtraction, or you can call it as addition, with what? the previous output of the XOR gate. So that means it is a delay network. The output of the XOR gate is delayed by a TB seconds and given as input. The present bit is actually XORed with the previous output of the XOR gate. Then again it is given to the DuoBinary coder. Okay. So here now just look at this. If AM, again AM is my input symbol, right? If AM is -1, then we set it as, if PM is 0, if PM, the pre-coded sequence is taken as PM here. Okay, pre-coded sequence means exactly here we get the PM. Okay, so based on this, if PM is 0, we set it as -1. If PM is 1, we set it AM as 1. That is again a polar representation of the signal. Or in general, we can set it as AM equal to 2 into PM minus 1. If PM is 0, we get -1. If PM is 1, 2 minus 1 is actually 1, right? So this same statement is implemented by using this particular mathematical equation. Now, what is PM? PM is the output of the XOR gate, which is nothing but DM. DM is, let me say, even though it is given as BK here, let me say DM is nothing but it is the data sequence. My input data sequence here is DM. Okay, so this is DM here. Let me say this is DM. Fine. And this is PM minus 1, right? Both are actually XOR or a modulo 2 addition or a modulo 2 subtraction, one and the same I say, actually only for binary case, remember, right? Both are XOR here. It's a modulo 2 subtraction symbol. Fine, it is nothing but XOR function. Fine. Now, what is BM is? BM is nothing but it is the output of the DuoBinary coder, right? Where we have a adder, no? We have the adder. Now, if I show you the diagram of that modulo 2 adder, the same figure, right? I have an adder here, okay, where this AM is the input here. AM and AM plus 1, AM minus 1, I'm sorry, the previous bit, both are actually added together, right? So we get AM plus AM minus 1. Now, what is this, just one second. Let me, yeah. So AM is, what is AM? AM is nothing but 2 PM minus 1. So 2 PM minus 1 plus AM minus 1 is nothing but it is 2 PM minus 1 minus 1, right? It is 2 times PM plus PM minus 1 minus 1. So that is BM. The output of the DuoBinary coder is nothing but 2 into PM plus PM minus 1 minus 1. So I have substituted AM and AM minus 1 from this equation. Okay. And from this itself, if I modify it, PM plus PM minus 1 is nothing but it is BM. Just bringing this 2 and minus 1 on the other side, we get BM by 2 plus 1. Okay, so the same equation is modified for PM plus PM minus 1. That's it. It is nothing but it is BM by 2 plus 1. Now, okay, I'll leave it this one. This is again PM minus 1 is nothing but it is DM. From this equation, DM, if I bring this on the other side here, DM is nothing but it is PM plus PM minus 1. Okay, that's all. So this is nothing but DM over here. That's it. This is DM. Okay. Now coming to the example, as I told, DM is nothing but PM plus means it's a modulo 2 addition. Remember, so DM is nothing but PM plus PM minus 1. Okay, and DM is nothing but again BM by 2 plus 1 modulo 2. It is modulo 2 is important over here to consider a modulo 2. Even though in the binary the modulo 2 is no need to perform a modulo 2, but when I go to the M-ary case, mod M is important, which again I will take up in the next slide. Now, just take the example. I have a data sequence. Okay, let us understand the concept by using this example. I have a data sequence here. Let me say 1110100. So whatever the data I have over there, right? Let's first of all pre-code the data, that is PM, right? What is PM? PM is nothing but it is the XOR function between the present bit and the previous output, right? This and this now. This present bit is XORed with the previous output of the XOR gate, and we get the current output of the XOR gate. So 1, 0 is 1, okay? Then we have 1 and 1 is 0, then 1 and 0 is 1, 0 and 1 is 1, 1 and 1 is 0, and so on. Okay, let us assign the polar representation to this. Let us assign the polar representation to this. 0 is represented as -1 and 1 is represented as +1 there, right? Then it is given to DuoBinary coder, where what exactly you are doing? You are actually adding the present voltage level with the previous voltage level. That is 1 plus of -1 is 0, -1 plus 1 is 0, 1 minus 1 is 0, 1 plus 1 is 2, -1 plus 1 is 0, -1 minus 1 is -2, right? Just go on adding, we get this level. Again, we are going to get 3 voltage levels, either 0 or +2 or -2. Same procedure as I explained earlier. What we have to do? We, in this case, just look at one, the unique feature of this particular method, where this BM is actually equal to 0 for the binary data 1. Just look at this. For a binary data 1 here, this is the binary data 1, I have 0 voltage level. For binary data 1, again I have 0 voltage level. What about 0? For 0, either it is plus 2 or minus 2. This is the unique feature of modified DuoBinary coder. Okay, in the previous method, DuoBinary coding, we were randomly getting the voltage levels, but here, due to the precoder, we have 0 volt for binary 1 and plus or minus 2 for 0. Okay, so here detection is very easy by using simple rectifier. Okay, if I use a simple rectifier where and threshold detector, if I use it over here, what I can say over here is 0 is always taken as 1, and when I apply this to a rectifier, say absolute value circuit, a full wave rectifier, plus 2 and minus 2 is represented as plus 2 only, right? Plus 2 and minus 2 is represented as plus 2 only. So we get only two voltage levels, either 0 or plus 2. If I pass through the rectifier, the voltage levels in the output of the rectifier is either 0 or plus 2. Okay. If I apply the same signal to the threshold detector, okay, where threshold value is set as the average of these two, say 1 volt. Okay. If the input is more than 1 volt, okay, that will be 2, will be taken as 0. If it is below threshold value, the output will be taken as 1. Okay. So this is how we are going to recover the original data by using this particular method. Okay, so this is the modified DuoBinary code where the symbol detection depends only on the current voltage level. Only on the current voltage level. So if this particular symbol detection depends upon only this particular voltage level. But in the previous case, DuoBinary signaling method, the symbol detection depends upon the previously obtained bit also. So that's why the error was propagating to the next symbols. Fine. Now, let us extend this particular concept of modified DuoBinary coder for M-ary case. Okay, so that is multi-level PAM signaling, that is M-ary PAM signals. Okay, where we are going to assign different voltage levels here, that is AM, is given by 2 PM minus M minus 1. In the binary case, it was 2 PM minus 1, that's it. But here, it is 2 PM minus M minus 1. Okay, in the binary, if M will be equal to 2, right? 2 minus 1 is 1, so it is 2 PM minus 1. That was the equation I used to assign the voltage levels for M different symbols. So in general, it is 2 PM minus M minus 1. Okay, and here PM is nothing but it is DM is a modulo M subtraction here. PM minus 1 of mod M. So mod M is important. Okay, PM is equal to, that is precoded data, is actually equal to DM, that is the applied data. Subtraction with the PM minus 1, take mod M. Okay, how exactly you are going to get the data? I'll explain with the example in the next slide. Okay, and possible voltage sequence DMs are nothing but 0 to M minus 1. Okay, now in the absence of noise, let us say BM is nothing but AM plus AM minus 1. Again, substituting those, AM as PM, this particular equation, I substitute for AM as well as AM minus 1. I will get BM as this. We can try this by writing in a rough book. Okay, substitute AM and AM minus 1 over here. That is AM as this, and AM minus 1 is nothing but 2 times PM minus 1 minus of PM minus 1. So I substitute over here. I'll get 2 times PM plus PM minus 1 minus of PM minus 1. Okay, hence, if I consider only PM and PM minus 1, what I'll get is BM divided by 2, okay, plus M minus 1. So that's what I will get here. Okay, and this is nothing but again DM itself, right? So DM is equal to BM by 2 M minus 1 of mod M. So mod M is not considered while writing this equation here. So mod M is very important. That is PM. DM is nothing but PM plus PM minus 1. Okay, of mod M. And if I substitute PM minus 1 as this particular equation, I'll get this. Okay. So now this is the basic concept we used for M-ary PAM signals, for a modified DuoBinary M-ary PAM signals. Now with example, let us understand this. Now, in this case, I have taken M equal to 4. Remember, M equal to 4 here. That means the possible voltage levels are, or data are, you are going to apply the 4 symbols with the 0, 1, 2, 3. Randomly, the symbols are taken. In the binary case, randomly, we used to take it as 0 and 1. But M equal to 4, with M equal to 4, the data consists of 4 different values like 0 to 3. In the random fashion, we have taken the example here. Okay, what is the precoded sequence? How do you get the precoded sequence? See this. The example for, the equation for getting the pre-coded sequence is PM is nothing but, that is the second one, the PM is nothing but DM minus PM minus 1 mod of M. Okay, that is, I need PM minus 1, again so I take this as the reference symbol over here. Okay, this is the DM, this is PM minus 1, so DM 0 minus 0 is 0, no problem here. While solving this, it's very simple. 0 minus 0 is 0, it's a subtraction, remember. In the binary case, binary subtraction is nothing but, modulo 2 subtraction is nothing but, it is XOR function or a modulo 2 addition, both are actually same. Again, coming back to this example, 0 minus 0 is 0, 1 minus 0 is 1, 3 minus 1 is 2, no problem. 1 minus 2 is equal to 3, this is what we have written here, right? 1 minus 2, actually 1 minus 2 is nothing but, 1 minus 2 is minus 1, right? It is minus 1. So, but there is no meaning for negative number. So, we have to take what? We subtracted 1 minus 2 is done mod M. So, we have to take the modulus of this particular number. Now, how do you take the modulus of this particular number? Just divide this number and take the remainder. That's it. Divide this number by 4 because M is 4. So, it is minus 1 times it goes. We get a minus 4 here. Okay. Then minus 1 minus of minus 4 is nothing but what? 3. So the remainder is 3, right? So 1 minus 2 is actually 3. This is the procedure. Okay. Somewhere else if I take again 3 minus 2, no problem, straightforward, it is 1, right? 0 minus 1. Okay, this is 0 minus 1 here. So 0 minus 1 is equal to what? 0 minus 1 is again minus 1, right? 0 minus 1 is, minus 1 means it is 3 itself. Okay, I'll take here 0 minus 2. Okay, 0 minus 2 is minus 2, right? So it is minus 2 divided by M is 4. Okay, minus 1 times again, minus 4 it is, minus 2, minus of minus 4 is 2, so the answer is 2. Okay, so that's what, that's how actually we get here. Fine, once again, let me erase all the things on the slides. Okay, now, so this is pre-coded sequence. I have got a pre-coded sequence here as this. Okay, and for 0, 1, 2, 3 we have to assign the voltage levels, like binary case we were assigning a plus 1 and minus 1. In this case we have to assign 4 different voltage levels. For 0 it is minus 3 is assigned. Okay, for 1 it is minus 1 is assigned, for 2 it is 1, and 3 it is plus 3. Okay, so wherever you have 3 it is assigned with the 3, wherever you have say 2 it is assigned with a plus 1. Okay, just look at this, it is plus 1 here. 1 it is minus 1 and 0 it is minus 3. It's a polar representation, let me say, for M equal to 4. Okay, now this is actually given to what in my circuit? It is given to the DuoBinary coder, right? In the DuoBinary coder, they are going to add the present symbol, okay, present voltage level with the previous voltage level. Just look at this, minus 3, plus of minus 3 is minus 6, minus 3, again minus 3 is minus 6, minus 1, plus of minus 3 is actually equal to minus 4, right? Somewhere here, minus 1 plus 1 is 0, minus 1 minus plus of minus 1 is minus 2. Okay, so this is what you are going to generate now. So this is the received sequence. It is written as received sequence, assuming that the same sequence is transmitted, same signal is transmitted, same is received. Fine. Now how exactly we are going to detect the symbols? Now just look at this, the possible voltage levels. We can have 0, minus 2, plus 2, minus 4, plus 4, minus 6 and plus 6. So these are the voltage levels, possible voltage levels in this particular case for a modified DuoBinary coder, okay, with 4 levels, M equal to 4. Okay, now by using these voltage levels we should be able to detect the symbols or decode the symbols, right? Symbol by symbol detection, that's what my title is, correct? Now how do you decode it? As I explained in the previous slide, this is the equation. So that is DM is equal to, or estimation is actually equal to BM divided by 2 plus M minus 1 of mod of M. Okay, so M minus 1 is nothing but 4 minus 1, right? 3, correct? So we have to add 3 to this BM by 2. What is my BM? BM is this, the voltage levels. Say I have at a particular symbol interval I received minus 6. Okay, that is my BM is minus 6. So minus 6 divided by 2 plus 3. Okay, plus 3 because M minus 1 I have, that is 4 minus 1 mod of 4. You have to take a modulus of 4 here. Okay, that is minus 3 plus 3 is 0. 0 mod 4 is anyway 0. Done. I'll take some other example. Say I go with a 4. 4 by 2. 4 by 2 plus 3. Sorry. One second. Let me erase this. Okay, done. I'll go with the pen. 4 by 2, 3 mod of 4. Mod 4, just do this calculation. 4 by 2 is 2, 2 plus 3 is 5. 5 mod 4 is actually equal to what? 1, right? 5 mod 4 is 1. Similarly, you calculate for 0. Okay, so 0 plus 3 is 3. 3 mod 4 is anyway 3. Minus 2 again. So minus 2, what is minus 2? Minus 2 divided by 2 plus 3. Okay, mod 3. Mod 4, I'm sorry, mod 4 it is minus 1 plus 3 is 2. 2 mod 4 is again 2, right? Now just compare. Before comparing, let me erase everything. Just compare this with this. Both are same. Okay, the original data sequence is actually received or recovered by using this particular equation. You can say by applying this equation, we have recovered that, this one. So this is for M-ary case. Okay, so one more example. Let me say this is how in the exam the question will be asked. Just go through the statement of that equation without precoder and with precoder. That means DuoBinary coder and modified DuoBinary coder. And we suppose that due to the error during the transmission, the level at the receiver input produced by the second digit reduced to 0. That means some error happens. How that error propagates? Okay, same thing you have to explain, whatever I explained in my video. So for this particular example, without precoder, this is what I'll get. Okay, now suppose this bit is in error. Okay, error actually propagates to multiple bits. This is what I have shown. Try to write this table on your own for this particular example. Okay, then create the error. Second bit is in error. So what will be the consequence on the other bits? That's what we have to check. How to overcome this? By using a precoder, even if there is a error will happen only in that particular symbol interval. Error propagation doesn't happen. These bits and these bits are same. Error propagation doesn't happen if I use a precoder or a modified DuoBinary coder. Okay, so in this video I have explained the two concepts of DuoBinary coding and modified DuoBinary coding. Okay, that is with precoder and without precoder. That is without precoder for DuoBinary and with precoder for modified DuoBinary coding. And how to detect the symbols, right? Thank you for watching this video.